Now, can you hear me? Yeah. Okay, excellent. Sriram, thanks a lot for that very generous introduction. It's a pleasure to be back after nearly 4 decades, not quite. And I'm really glad to see lots of young colleagues here. And it was really one of such lectures that motivated me to do physics, and I'm very happy to share the thrill and the fun that that was brought to me by working in this particular area. Today's talk is going to be in 3 parts: new discoveries, puzzles, and prospects. But I thought, just in case there is somebody who may not have heard about gravitational waves, which is very, very rare, I'll give you a brief introduction of what gravitational waves are. So let's start. That's not a simulated sound. It turns out that's the sound of the cosmos. The sound of the cosmos, meaning ripples in the very fabric of space-time, produced by black holes colliding. It's a blast that travels at the speed of light. And in 2015, we made a discovery in twin LIGO detectors, laser interferometer gravitational wave observatory. That's what this acronym stands for. If you look at the signal in the two detectors, they're almost identical. And I'm going to talk a little bit about what it means and for the detection probability and so on. Now, for this discovery, in 2015, the event is called GW 150914. GW stands for gravitational waves. 15 is 2015. 09 is September. And 14, of course, is the 14th day in September. You will see a few more such telephone numbers as I go along, and that's the meaning of this event. So it's a which lasts for about, in this particular case, only 200 milliseconds, but it could last for a few seconds to a few minutes. But towards the end of the talk, I'm going to argue that we want to build detectors in which we can watch them for hours and days. That's the final goal. For this discovery, my colleagues Rainer Weiss, Barry Barish, and Kip Thorne were awarded the 2017 Nobel Prize. The citation reads for decisive contributions to the LIGO detector and the observation of gravitational waves. But in reality, this work was done by hundreds and hundreds of PhD students, postdoctoral fellows, and without their wonderful effort, we wouldn't have detected gravitational waves. A gravitational wave observatory is an Michelson interferometer, typically, and you see 3 of them here. The top 2 are in the United States of America. The top one here is the LIGO Livingston Observatory, and the middle one here is the LIGO Hanford Observatory, and both of them are 4-kilometer arms Michelson interferometers. And the bottom one here is the Virgo Observatory in Pisa, Italy, and that's about 3-kilometer arms. With these observatories, we are now able to detect black hole and neutron star collisions routinely. Not neutron star collisions so much, but black hole collisions. So as you can see, there are people all around the world here, including institutions from India. So India is a very big contributor. As some of you might know, there is an extremely active group led by Chandra here, Professor Chandra, who is working on developing algorithms, waveforms, in order to understand gravitational waves. I'll start with, in my part 1, about discoveries, starting with the very first discoveries and what they told us, and the more recent ones, and then I will go on to the other 2 parts. So this is the first part. The very first detection, of course, was that I mentioned to you already. And this was discovery of a pair of black holes that came and collided. And in the process, we observed the formation of a new black hole with a pretty clear evidence, but I wouldn't call it conclusive evidence for black holes for reasons I will tell you later. But this is as good as it gets in detecting black holes. So although black holes are black, interacting black holes are not black. They do emit gravitational waves, and that's what we observed in 2015 for the first time. But not only that, this detection gave us black hole masses that was somewhat unexpected in astronomy. Astronomers thought that black holes of masses greater than about 20 solar masses cannot exist by star formation. And so they had to revise their models, astrophysical models. And one of the things that they did was to say, okay, we don't really understand what is called the metal component in the universe. And they had to say, oh, by the way, for astrophysicists, anything heavier than hydrogen is a metal. Helium, carbon, oxygen, they're all metals. I don't know why they call them metals, but I had to revise this thinking, because if you have what is called low metallicity environment, then you could see black holes. And that's something that they had to revise after this discovery. The first two observing runs between 2015 and 2017, August 2017, we discovered 10 binary black holes, but it also gave us the first binary neutron star called GW170870. This is a crown jewel in the discovery of gravitational waves, unlike anything we have seen until now. Even today, it happens to be a crown jewel in our field. Well, it's not just a single discovery. This was the first detection of a binary neutron star merger ever detected. And it began a new era in multi-messenger astronomy. Multi-messengers are those that emit not only gravitational waves, like the binary black holes, but they also emit electromagnetic radiation in the entire electromagnetic spectrum, from gamma ray bursts all the way to radiance. And they are messengers, not just multi-band, which they would be if they emitted just optical and X-rays. You know, they are two different bands, so they're called multi-band astronomy. That became very famous in the 60s and the 70s. But multi-messenger astronomy started with, of course, cosmic rays, but later on, supernovae, 1987A supernova was one such. But this is a completely different game, as you will see later on. Now, this detection confirmed for the first time, it was predicted by Einstein's theory, that gravitational waves travel at the speed of light. But here we have a confirmed speed of gravitational waves, the same as speed of light. Why? Because simultaneously with gravitational waves, we also received gamma ray bursts produced in the aftermath of the merger. And those gamma ray bursts came to us only 2 seconds after the end of gravitational waves. You cannot produce any electromagnetic waves in the process of two neutron stars going around each other. Electromagnetic waves are produced initially by what is called a prompt emission process, in which there is a central engine which is blasting out jets of gamma rays. And later on, the material that neutron stars are made up of, which are neutrons, of course, go through what is called nucleosynthesis, producing heavier and heavier elements. And these heavy elements decay, some of them, and in the process produce these decay ejecta, and that is what we observe as what is called kilonova. And this kilonova was, for the first time, observed in the aftermath of this binary neutron star merger. But that also helped us observe the the gamma ray bursts, which confirm speed of light. Turns out these are prodigious sites of the formation of heavy elements like gold, platinum, lanthanides. A lot of material that we today use in technology couldn't have come from just stellar evolution. Stars produce elements up to about iron, iron 56. After that, in order to produce, you need to push the nuclei with much greater energy. And consequently, you really need extremely energetic processes such as collision of neutron stars. And it's only there, some of you may be wearing some gold chain or whatever, that must have come from that neutron star collision that took place some hundreds of millions of years ago in the neighborhood of the solar system. Probably not hundreds, it could be billions of years actually, even before the formation of the solar system. It would have got mixed with the interstellar medium, and that's what is available to us today. So without neutron star collisions, advanced civilizations couldn't have existed. Now, this also turns out to be an event that gave us a new tools for measuring distances accurately. Okay. I'm here at this point. Tool for accurately measuring distances. And this is because in general relativity, the amplitude and luminosity of gravitational waves is dictated by a few parameters of the binary that we are observing. Their masses and how the frequency is changing as a function of time. It turns out we can measure both the apparent luminosity and the absolute luminosity of gravitational waves, and from that we can infer what the distance to the source is. There is a curse in this measurement, which is that we don't really know the inclination angle of the orbit, and that makes it the error in distance a little bit too large. However, this is as good as it gets. Astronomers have to have a very detailed modeling, and a lot of the time they don't know the systematics. And here the systematics are very well in control, and we, for the first time, were able to, with a single measurement, we were able to measure the Hubble constant, because if you know what is the distance to the object and you know the redshift, measure the Hubble constant. And that gave us the posterior distribution of the Hubble constant. I know people at the back may not be able to see this graph. It's something, between 50 here and about 120 there. That's the kind of measurement that we made. That might look too imprecise. This is just what, with the very first source that we detected. And the mode of the distribution is entirely consistent with two other measurements of the Hubble parameter, the rate at which the universe is expanding today. One of them comes from the cosmic microwave background. It determines not only H0, the current expansion rate, but also 6 other important parameters in cosmology. But the measurement that comes from supernovae, which are standard candle, doesn't seem to agree with the one that comes from the microwave background. And this is termed as the Hubble tension. And it is largely expected that gravitational waves might be able to resolve this tension. Perhaps there is some systematics in the measurement of the supernova distances. It's not, after all, a standard candle, or maybe there is a bias. Or the CMB may be a different value because there is new physics in either cosmology or fundamental physics, and that is giving us a different value here. So gravitational waves might be able to resolve this problem because we don't suffer from, as far as we understand, any systematics in the same way as the supernova measurements do. So this is one of the key goals for building even better gravitational wave detectors as we go along. The final jewel in this crown is really that of understanding equation of state of ultra-dense matter. This is a quest I began when I was a student here, and I was asked to prepare for a seminar by Professor Balakrishnan, and what I did was to look at black holes and neutron stars. I was absolutely puzzled the behavior of neutron stars. At that time, only 2 decades was still not known, and after nearly 6 decades of the first discovery of neutron stars, we still don't completely understand what neutron star cores are made up of. They could be made up of hadrons, which is confined quarks, mostly neutrons, a little bit of electrons and protons, or they could be composed of free quarks. Free quarks because the density is so high, a few times 10 to the 17 kilograms per meter cube, that quarks are squished out of their constituent matter like neutrons. We don't know which one it is, and that's something that gravitational wave detectors will be able to tell us. And if somebody has a question about how that is done, we can talk about that later. Today, after the 3 observing runs, these are the binary black holes, neutron star black holes, and binary neutron stars that we have discovered so far. There are about 90 events in total. They're all in blue, or this yellow or orange. The blues are binary black holes. Every one see a pair of objects merging to form a bigger black hole. The x-axis really does not have any significance. The y-axis is showing you the masses in units of solar masses, 1 to about 200 solar masses. So these black holes merge together, they form a heavier black hole. These 2 black holes merge together, form a heavier black hole. This is what we have observed so far. And it consists of all 3 families of compact objects: binary black holes, neutron star black holes, and binary neutron stars. Radio observations have already given us a plenty of binary neutron stars, or neutron stars in general, whereas they also have given individual black holes, individual neutron stars. They never observed binary black holes or merging binary neutron stars. Just binary neutron stars, yes, but not merging binary neutron stars. So this has opened up a completely new area of research. What does this population tell us? What we did was to take only 76 events out of the 90 that I mentioned in order to determine the properties, because you want to have a pure sample. You don't want to contaminate your sample with some noisy events. If you take the false alarm rate less than 1 per year, then the catalog contains 2 binary neutron star events. I mentioned one of them. The second one was discovered during the 3rd observing run. And then we have 22 confident binary black hole events and 2 neutron star black hole candidates. One of them is certainly astrophysical origin. The other one might be instrumental noise, or it could be a binary black hole candidate. We don't know. From that population, we can actually measure what's the rate at which these binary black holes and neutron stars merge. That's an important astrophysical information. And what we know are binary black holes merge about 25 times per year within a 1 gigaparsec. 1 gigaparsec is about 3 billion light years. That's the volume with which we are making this merger rate. Now, before LIGO discoveries, that number was unknown by 5 orders of magnitude. So that's the progress we have made in the calculation. Binary neutron stars are still uncertain by 2 orders of magnitude, but we know them to within a factor of about 100. But before LIGO made the discoveries, they were 5 orders of magnitude. And finally, neutron star black hole merger rate is in between those two. Why is this all important? It is important in order to understand what is the kind of things that we can detect as we improve detectors and how to test astrophysical models with these kind of observations. That's the reason why they are important. Something happened. I think I pressed the wrong button. The source of uncertainty is simply because we don't understand quite what is the volume up to which we can see, because the detector certain sensitivity which is very. So we haven't really observed that many systems. We have observed only 2.
So it suffers from small number statistics.
And finally, the other thing is that
all these rates depend on probably the masses,
and we can't measure the masses very well. So there are several uncertainties that are correlated, which go into this uncertainty. By the way, I just wanted to mention, please stop me at any point. During the lecture, you can raise your hand and you can stop and answer your questions. I really very much like to do that instead of talking for the full hour. One very important aspect is that we seem to see some structure in of masses, and this is critical for cosmology and population synthesis models, and I'm going to probably do that at some point. Peaks around about 7.8 solar mass and 26.6 solar mass, and a gap of 10 to 20 solar mass. Let me actually show you a picture corresponding to this. I think it's, yeah, this is the picture that shows you density of what is called the chirp mass. It is related to the total mass of the binary. Here it is in terms of solar masses, 5 to 80 solar masses. And these are the distribution of each of the events. And when you combine them all, you get what is called the events posterior. This is the observed distribution of these binary black holes. And there seems to be this structure at something like 8 solar mass, and one also around 18 solar mass. And these are helpful in understanding the populations, but also cosmology. Now, in addition to these populations, we have some exceptional events, and I want to talk about some of them. I already told you about 1509-14. This is the first discovery, 1708-17. This is the third discovery, which finally settled that we are routinely observing binary black holes. But I'm going to talk to you about these 3 events. 1904-12 is an event in which we have a small black hole in orbit around a big black hole. In general relativity, if you take 2 black holes, equal masses, and you rotate them by 180 degrees, you essentially get the same system. Consequently, gravitational wave frequencies are 2 times the orbital frequency. And the signals that we observe are 2 times the orbital frequency. But if you take one of them big and the other one small, when you interchange after a rotation of pi, you don't get the same system. So you have to, then the gravitational wave signal accordingly will also contain 1 times the orbital frequency, 2 times the orbital frequency, and all the harmonics. And the first time, because of the mass asymmetry, we were able to measure not only the quadrupole radiation, but also the octupole radiation. Simulation of those 2 systems, they're producing a very long waveform, and in the process, they do have some harmonics. And I'll show you another system, it is even more spectacular. So what we learned from observing this system is that, first of all, it was observed in all 3 detectors. And the first black hole binary system in which we definitively have unequal masses, which is important for this higher harmonics. The 30 solar mass primary merged with the 8 solar mass companion. And then the significant non-zero spin of the primary, that was also a first discovery. And finally, the dimensionless magnitude was about 0.2 to 0.6. This higher harmonics allows us to test general relativity in new ways in the strong field sector of the theory. Such tests are not possible with any solar system experiments or other astrophysical observations. That's correct. So the way this is done is to use a waveform model that consists of all the modes, not just L equal to 2, but L equal to 3, L equal to 4, all equal to, minus L to plus L, and then see how much of energy is there in each one of them. This system, second one that I'm talking about, GW 190814, is even more mass symmetric. The only reason why I mentioned the other one is because that's the first or the higher modes. But this system, which consists of 23 and solar mass and 2.6 solar mass, merged together to produce a 25.6 solar mass. And this system is even more interesting. This is a system in which the mass ratio is almost 10. And whenever it is mass asymmetric, it's going to generate higher modes. And this spectacularly reveals the higher modes that are present in the system, the octopole that I mentioned. But more importantly, for the first time, we discovered an object that has come to be known as a mystery object. Why? Well, in astrophysics literature, you cannot form a black hole, it's believed, less than about 3 solar masses due to stellar evolution. And neutron star masses have been measured by astronomers, radio pulsars, or X-ray pulsars, and the best measured, or the greatest mass, is about 2 solar mass. Moreover, from binary neutron star observations, we know that the maximum mass of a neutron star, this is just the probability density as a function of mass for neutron stars, they seem to indicate that you really should not have any neutron stars of masses greater than about 2.3, 2.4. But this one happens to have a mass right here at 2.6 solar masses, and this is the first, maybe the heaviest star that we have discovered, or the lightest black hole. We don't know which one. So it's a mystery object for that, but that can be resolved with future observations. Moreover, this is the first time we have measured the spin primary with exquisite precision and exquisitely zero. The black hole is not spinning at all. And thirdly, we have been able to clearly see the signature of the higher modes. This is almost like the first experiments conducted after electromagnetic theory was proposed. Electromagnetic radiation is dipole. But you can also generate quadrupole. You can generate octupole. And here, for the first time, we can see the quadrupole, if it contained only quadrupole radiation, it would be a monotonic increase in frequency and amplitude. But in this case, we have a modulation both in frequency and amplitude. And that's the signature that we see here. You want me to stop or continue? Is okay? And this is the final thing that I'm going to talk about, the individual systems. It's called GW 190421. And it consisted of an 85 solar mass black hole merging with a 66 solar mass black hole, producing a 142 solar mass black hole. You must have seen in all those slides, the total mass is less than the component masses. In the process, merger, something like 8 solar mass multiplied by c square was converted into pure radiation. So gravitational waves are the best converters of mass into energy. We know of no other process. And in fact, Stephen Hawking estimated that you could extract something like 33% of the total mass. And today we know from numerical relativity simulations that it's probably about 10% of the mass can be extracted. But this is not quite there. Right? This is about 142 and it's 8. But it's pretty much the best way you can extract energy. It is. So with this, let me now tell you what's going on. This is the 4th observing run, which started earlier this year. And advanced LIGO is now working at design sensitivity. Unfortunately, the Virgo detectors are off at the moment because of technical problems. And now we are able to observe binary neutron stars up to 160 megaparsec. During the O4 run, we have not detected any binary neutron stars so far. However, we are observing binary black holes almost several times a week. If you have a mobile phone, you can actually subscribe to LIGO alert system. And every time they go off, you get a signal on your phone. I suggest that you turn off the phone if you subscribe to it during night times, because it will disturb you. It will start making loud noises. However, this is the thing that we do. We are always hooked on to this alert system. And within few minutes of observing, we are getting alerts. And not only just us, anybody can subscribe. You don't have to be part of LIGO Scientific Collaboration. And astronomers routinely go and turn their telescopes to the sky to make those observations. This is what is called the sensitivity curve. It's a bit technical. I'm not going to say too much about it, except to say that this was hand-drawn something like 25, 30 years ago by Ray Wise. And it turned out that sensitivity has finally been achieved. And it's a heroic engineering as well as scientific achievement for our field. During the 4th observing run, we have observed a total of 64 binary black holes. All of them are boring binary black holes. Okay? Not binary neutron stars, which are much more interesting. And in total, we have now 154 systems. This is the alert system that I talked about. That's also a link to a website. You can't read anything from that. I'm just saying that kind of information that you will receive when you go to the website. And we are accumulating more and more binary black holes. And that's a treasure trove of data to learn about the universe. But LIGO has had its own puzzles with these discoveries. And I'm going to list a few of them. Although I mentioned to you that in principle we can measure what the structure of neutron stars is, we are nowhere near doing it. We don't know whether neutron stars are composed of confined quarks or free quarks. We don't know how heavy neutron stars could be. Or we don't know whether neutron star mergers are the only things that are needed to produce the heavy elements in the periodic table. Or do we need other mechanisms to produce them? And it's a puzzle mostly because when I was growing up learning about stellar processes, I was told that we are all made up of star stuff, and all the technology that you see around us is because of stellar evolution. Not true. You actually need binary neutron star mergers to produce elements in the bottom part of the periodic table. That's what we produce. But we don't know whether the other alternative sources are needed. And we don't know how binary neutron stars form and evolve. That's a very big question for astrophysicists and almost an embarrassment, because we don't know the locations or the detailed mechanism of how they form and evolve. I'm posing these questions because those are the ones that we will be able to answer with future observatories. Let me mention the questions that arose with that GW 190521 is that the masses are so large that they shouldn't exist in nature. This is what is called the upper mass gap in astrophysics. No matter how heavy the progenitor star is, you can't produce a black hole at the end of stellar evolution, a mass that is more than about 60 solar masses. So if these exist, where did they come from? My friend here might tell me, oh, they formed by merger of black holes, and those merger are merging again. But such processes are very rare. Maybe 1 per 1,000. But we have detected only 90. We're already observing, several of them now. And that's not possible. So one possibility is that maybe these black holes formed in the early universe, they're called primordial black holes. And that would be super exciting, because that was one of the things that was proposed. Not this mass range, it turns out. There are severe constraints coming from CMB. Yes, we can constrain, but whether our constraint is tight enough is not clear. I think CMB can constrain them better. However, LIGO Virgo observations can constrain subsolar black holes even better. Nobody else can do it better than us. Even 1 part in 10,000 of the energy density in gravitational waves, in mass black holes can be constrained. Yeah. Oh, prejudice. Why they should not exist? There isn't any. No, there is no prediction at all. There is no scale, right? Oh, that is coming from astrophysics. So what happens is, if you take a very massive star, and then at the end of the nuclear fuel, the whole thing collapses, and there is such a massive amount of energy production, there is pair production, and that leads to an explosion of the whole star, and most of the material is ejected. What remains is going to be always less than 60 solar mass, even if you started with 1,000 solar mass progenitor star. And this is what is called pair instability supernova, because the pairs are produced, electron-positron pairs are produced, and they combine, and they blast out the entire star. That's the reason why it's a problem for producing black holes in that mass gap. Okay. Now, one of the puzzles to me, theoretically, is that most of these black holes seem to be having zero spin. I don't know why. And this is just the black hole spin as a function of chirp mass. Those are the contours, and they're all touching, most of them. There are 1 or 2 exceptions. But that's a puzzle as to why they are non-spinning. Penrose process could possibly do that, but in order to do that, you would need some accretion disk or something to go in. But what happens when you form 2 black holes, if we put them together, it drives away all the accretion disk. There is no way to produce them. The other mechanism is similarly a boson cloud around a black hole could form what is called a gravitational atom, suck the rotational energy out in the form of gravitational waves. That's another mechanism. But once again, a binary is not an environment that is conducive for forming these clouds. It can form in isolated system, but not in binaries. And there is a good reason for it. It's just simple Newtonian calculation that tells you you cannot have accretion disks around black holes. That's the reason why. To me, it's a puzzle as to why this is happening. But how do we form black holes? Similar to binary neutron stars. How do we form black hole binaries and evolve them? What are the main channels? That's another big question. And can black hole mergers lead to electromagnetic afterglows? After GW190521, astronomers looked at their data later on and found that there was a burst of radiation coming in from the same sky, and they put the probability of that happening by accident at something like 10 to the minus 3. But since then, nobody has detected anything. But it is a big question whether binary black holes can lead to electromagnetic afterglow. And what's the origin of these greater than 50 solar mass black holes? This is the pair instability supernova that I was talking about. They shouldn't really exist. If they existed, maybe they're forming from hierarchical mergers. That may be one solution, but that is still puzzling because there are too many of them. Yeah.
What would be the source of these afterglows?
In the case of GW1905, holes merged, they produce a kick, and that kick is, when the remnant black hole pointing through the interstellar medium is shocking. The interstellar medium producing this electromagnetic radiation. That's one model that seems to be there, but most relativistic astrophysicists don't believe in that. They cannot produce, you really need extreme environments to produce it.
Is it the Unruh effect?
This one? No, it is just shocking. This is a black hole that's just going through the interstellar medium that is shocking, accelerating particles that is producing it. It's just a, Bremsstrahlung or, yeah.
But it
Yeah.
needs a charge, right?
Yeah, the interstellar medium contains both charged particles as well as, neutral particles. So this is a mechanism that's not really understood. People have coincidentally observed, and whether or not these mechanisms work, my relativist astrophysics friends tell me that it is junk. This is not going to work. However, it's interesting if such a mechanism works. We should really be open in our understanding of what's going on. And one thing that I have been saying all along my lecture is that, these are black holes. We discovered 90 black holes. That is really not based on a smoking gun evidence for black holes, which is in the form of what are called quasi-normal modes. When two black holes merge together and produce this highly deformed black hole, it settles down into its final quiescent state by emitting an infinite spectrum of modes called quasi-normal modes. These quasi-normal modes depend only on the mass and spin angular momentum of the remnant, nothing else. Chandrasekhar called black holes as the simplest macroscopic objects that you can ever think of. This entire thing is characterized by only its mass and spin angular momentum, and even its vibrations. That we have not seen. We have seen only one mode, the quasi-normal mode, only what is called the 2-2 mode. But in order to confirm that they are black holes, we must see the higher modes. In addition to all these puzzles raised by LIGO observations, we have other problems in theory and observations. I'm going to be extremely quick with this because of, we are running out of time. The black hole information paradox, the black hole singularity, which is a huge embarrassment for general relativity, and the lack of a viable quantum gravity theory, the accelerated rate at which the universe is currently expanding, and the nature of dark energy and the origin of dark matter, the Hubble tension that I mentioned, which is disagreement between two very precisely measured expansion rate, and finally the origin of supermassive black holes. They're all really puzzles in cosmology and fundamental physics. Now, there are prospects to resolve all these things and learn more about the universe. And that's my final part in the next 5 to 10 minutes. On the one hand, we have LIGO coming up. When that joins, our ability to localize sources and follow them up with the telescopes is going to increase by at least factor of 5 to factor of 10. And that's extremely important when LIGO India joins that network. We now have the project fully funded, and the construction has begun, and we hope to have the detector in the next 10 years. This will be joined by, for sure, the Laser Interferometer Space Antenna, which is a European project, and it will observe binary black holes in an entirely different window in the millihertz band and supermassive black holes. So that's another development. In addition to that, we are now working on 2 projects. Cosmic Explorer, which is the next generation observatory in the US, and Einstein Telescope, similar effort in Europe. I've been lucky to be involved in all 3 of these a little bit about 10 years ago. As I mentioned, this is already now, LIGO India is already approved. On May 1st, 2023, we got the award, and it's going to be completed within the next 8 to 10 to 15 years, depends on the progress that we can make with this. So I won't say too much about that unless you have some questions we can answer. I'll say a little bit about Einstein telescope. It's a triangular detector, underground, and 10 kilometers each. The reason why we want to build larger detectors is that the arm length of a gravitational wave detector is similar to the diameter of a telescope. Bigger the diameter, greater is the collecting area. Here we don't collect gravitons. However, the sensitivity increases in exactly the same way. And by making the detectors bigger, we can observe sources farther, but also with greater signal to noise ratio. And Einstein telescope will host 2 interferometers in each of its arms to build what is called a xylophone detector. But they also have 3 V-shaped detectors, right? And consequently, they will accomplish phenomenal sensitivity by more than an order of magnitude when they come online in about 10 years. Now, the frequency range is similar to LIGO, but much better improved sensitivity at lower frequencies, maybe starting at 5 hertz or so. There are 2 candidate sites now. One is in the Netherlands, and the other one is in Sardinia, Italy. And both of them have promised money, both governments. Not the entire money. These are going to cost $2 billion each. Right? Each Einstein telescope will cost that much. But each of these have only promised a fraction of the total money. So the other have to contribute. And also there is a debate whether to go from this triangular shape to 2 Ls, one in Sardinia and one in Netherlands. The debate is still going on, and I have been involved in some of those studies, but we don't have the final decision yet. The one that I'm even more deeply involved is Cosmic Explorer, which is 10 times bigger, 40 kilometers, 10 times bigger than LIGO. And it's going to be a ground-based observatory. Turns out that it's not so difficult to find space in the US. There are lots of places in Montana, in Nevada, desert, and so on. So we have to find several such sites. And Cosmic Explorer is as I said, next generation US concept. A 40-kilometer detector, one somewhere in the Montana region, and another 20 kilometers somewhere deep south. That's the goal. And with these kind of observatories, achieve 10 times better sensitivity than LIGO. And to just compare what happens with astronomy, maybe I should come back to that in a minute. So Cosmic Explorer is envisaged as a National Science Foundation project. The Horizon study is complete. Since this audience is really not in, probably don't care too much about programmatics, I will skip the programmatics part and go. We have completed what is called the Horizon study. We have been awarded $14 million to carry conceptual design study, which is still a paper study. And I recently advertised a postdoctoral position to come and work on the design study of Cosmic Explorer. So I think this is absolutely not needed. So we don't have to talk committees and so on. So I'm going to skip this. We submitted a white paper which contains even more information. But I want to tell you about what Cosmic Explorer can do. On the left-hand here, you see the age of the universe. This is the birth of the universe. And this is now, today. And this is the redshift, which goes from 0.01 all the way to 1000. The universe started at infinity, of course, z equals infinity. Oh, I have to somehow stop this. Now, as you can see, at the raw sensitivity, we are able to observe sources at a distance of redshift of 100, and the universe was only about 20 mega-year old at that time.
For comparison, today our instruments are only able to observe sources around this distance.
So it's an enormous increase. Optical telescopes took about 300 years to accomplish this vast increase in sensitivity. The reason why we can do this is because we are sensitive to what is called the strain or amplitude instead of intensity. Now we are also, yeah,
Talking about compact objects.
yeah,
Compact objects.
only emerging compact objects, yeah.
Then, most of the universe is still not yet non-linear, so there may not be many objects.
Oh, I'll tell you how many events we are going to observe just in a minute. So now if you look at what kind of systems we might be able to observe, here is the population of systems that LIGO has observed so far.
GW 150914, first discovery, 1905-21, the mystery object.
You can see we will observe them with exquisite signal to noise ratio. Several thousands for this, about 1,000 for this. That is astronomers, you have to square that signal to noise ratio. Okay. Now, the other objects that you can observe are binary black hole population. You asked me what kind of population exists. Well, we see something like 200,000 binary black holes per year. What about neutron star black holes? Well, maybe a similar number, but what is even more impressive is the binary neutron star population, and we will have the sound that you heard. There will be one going off every minute. And we'll observe something like 2 million binary neutron stars every year. And there will be several hundreds of them passing through the detector band every minute. We can do enormous amount of science using those. This left plot shows you what is called the donut plot, the reach of advanced plus detectors, which will be operational in about 2 or 3 years. I've not even plotted the advanced LIGO here because it's
even more inside.
And then we improve the detectors once more, LIGO detectors. It's called A-sharp. And then this Einstein telescope and Cosmic Explorer. This is the population from what we know today about astronomy, but there could be primordial black holes beyond this region, in this region, and we will be able to observe them.
This is
what I call science field. And mainly there are 3 things: dynamics of dense matter, how matter behaves when the extreme conditions, extreme gravity and fundamental physics, and black hole and neutron star populations throughout the universe. So with that, let me stop, and if there are any questions, I'll be able to, happy to answer. Thank you.